Namaskar friends. So we are now into lecture 14 of our course on product design and development, and we have divided the total discussion into 4 weeks, and we have already completed week 1, week 2, and we have discussed the basic concepts of product design and development. We have considered the functional aspects of product design by specifically addressing the problem from the value engineering point of view. We have already seen the examples of value engineering. In third week, we are trying to learn certain important tools which help us in the product design process. In first lecture, we have learned an important tool through which we take the input from the customer and try to match that input with the technical specifications of the product and try to benchmark our product in comparison to the products of the other companies and try to take certain important decisions related to the product design process. That tool was discussed, that was quality function deployment, and we have discussed the house of quality. In second lecture, once we have the voice of customers, we know what customers want, we know how technically we can meet those specifications or those requirements of the customers, we go for the actual design of the process, and therefore we considered an important design tool, that is computer aided design, in which we have seen what are the steps involved in computer aided design, and we have also seen that what are the important softwares which are used for solving or designing the problem using the help of computers. We have also seen that today the computers are not only used for drafting the problem or for sketching or giving the geometry to the problem. Softwares are also helpful in analyzing and providing solutions to the engineering problem. So, the CAD discussion helped us to have a basic understanding about the tool and how it is helpful for the product design process. In third discussion or third lecture on week 3 or in week 3, we have discussed the robust design procedure and how we can differentiate between the controllable parameters and the uncontrollable parameters, and we have concluded that it is our duty to ensure that our product is insensitive to the variations in the noise factors, and therefore only the product will be usable for the customer and it will be acceptable in the market. So, with this background, now we are slightly moving towards actualizing our product. We can conceptualize it from the customers or from the demands of the customer. We can design it on the screen using CAD. We can put certain things into the product. Certain things means the robustness. We can put the quality into the product by appropriate selection of materials. Now we have to see that when we are actually going to fabricate or manufacture the product, what are the things that we have to keep in mind. So, we have to design the product in such a way that when it is manufactured, it is easy to manufacture. We are not doing a course on manufacturing technology in which we will learn the various processes like primary forming and deforming or material removal processes. We are not actually producing the product, but we are actually designing the product, but during the design stage only we have to ensure that it is easy to manufacture or fabricate or assemble the product at a later stage. So, during design only we will ensure that all these conditions are met, and for that we have to ensure that our design is excellent, and DFX is an important term that is used nowadays, that is design for excellence. So, excellence not in terms of performance or quality or reliability or durability, but excellence in terms of manufacturing also, in terms of cost also, in terms of assembly also. So, we have to ensure that the product design is excellent in nature. Now, from where the terms X come into picture, let us quickly go to that. Now, design for excellence, generally it is called as DFX. Design for excellence or DFX is a systematic design approach that entails wide range of guidelines and standards. So, first thing is, it is it entails wide range of guidelines and standards. We will see examples of one or two such guidelines today with a specific example or a specific application. So it entails wide range of guidelines or standards. So we can also say that DFX is a set of guidelines and standards which we should follow during our design process. These are focused on optimizing the product realization life cycle. So these guidelines are helpful to us to make our product successfully, in order to make our product economically, as well as helps us to actualize the life cycle of the product, or to some extent we can say to minimize the life cycle of the product. In reality, the term DFX is better thought of as design for X, where the variable X is interchangeable with one or many values depending on the particular objectives of the venture. So we can say it is DFX. X can take any value. So X can be manufacturing, it can be assembly, it can be quality, it can be reliability. So DFX then becomes design for manufacturing, depending upon what is our area of focus. If we are focusing on the design which we want that it should be manufactured easily, we will say design for manufacturing. If we have a design at hand which we need to assemble easily, we will say it is DFA. So X can take any value, but in general DFX means design for excellence. Now here in this particular point, I have emphasized on one thing, that these are set of guidelines which helps us to actualize our product. Also it helps us to save some time. So this can be explained from another point of view, that in previous, you can say, business environment, usually the design center will be ascertained or will be assigned the task of designing the product. The manufacturing facility will only be used to manufacture the product. Now there are two separate entities, the design center and the manufacturing facility. Now the design center will design the product based on the knowledge base of the designers and the requirements of the customer. Now this design may be in the form of drawing sheets, will be sent to the manufacturing facility for manufacturing the product or for manufacturing the prototype. But there may be certain guidelines or certain set of rules which have been violated by the people who are involved in the design center. When this design reaches the manufacturing facility, the manufacturing engineers or production engineers will highlight, maybe in many cases they will send the design files back to the design center with their comments that these are the we can say features or tolerance requirements which cannot be achieved by the manufacturing facilities available, and then therefore it has to be redesigned. Now once this design or in the form of drawings reach back to the design center, they will see, redesign the product and again send it back to the manufacturing facility. So this iteration may be a single iteration, it can be double iteration, 3 times it may happen, but it takes or eats away lot of precious time which has to be controlled or completely eliminated. So in the present context, there is no company in which the design center will be a compartmentalized center or will be an independent center. These days, for launching a new product into the market, there will be a product team in which there will be individuals from marketing, sales, finance, engineering background, then production, design, legal, different people with different specializations will comprise the overall product team, so that all these problems of iterations are taken care of, and the design team, when it gives the product or the design of the product, it is final in all its aspects and it is not sent back from the manufacturing facility to the design team. And the role of information technology cannot be ignored in achieving this thing or this particular objective. So the DFX, DFM, DFA, DFR or DFQ, all these are concepts which want or which aims at reducing the overall cycle time for launching or overall product design time for launching the product into the market. So we can see that if we use the concepts of DFX, our product design will be not only robust in nature, but will also save lot of time for the organization, and the manufacturing cost will also be optimized. So we will try to see that how the concepts of DFX can help us achieve our objective. So this is the first I think I have explained it, that how DFX is not only helpful in giving us a robust design, but is also helpful in saving lot of money also for us, as well as saving lot of time for the organization. Now these guidelines ensure the issues related to manufacturing. I have already told cost, quality, assembly and serviceability are addressed at the design stage only. So our design will be good in all these aspects. If these guidelines are not adhered during the design stage, it can lead to engineering changes occurring at later stages of product life cycle, which are highly expensive and can cause product delays and cost overruns. So I think whatever I explained in the initial discussion part for today's discussion are completely outlined or are explained in a much better manner in these sentences, that if we take care of these guidelines, we achieve good manufacturing, low cost, high quality, easy assembly and good serviceability if we adhere to these guidelines. If we do not adhere to these guidelines, it can lead to highly expensive product delays and cost overruns. So we are losing on all accounts if we do not follow these guidelines during the product design process. Now this is a very good diagram. You can see some of the common substitutes for X, as I have told, design for excellence, design for X, X can be substituted. So here are few examples: design for manufacturing, design for assembly, design for manufacturability and assembly, design for production, and on this side you can see design for cost, design for service, design for safety, design for reliability. So X can take any name, but the overall objective of the product designer is to ensure that the product is good quality, low cost, easy to manufacture, easy to assemble, is reliable, is easy to service. So when you take into account all these things, then it means you design for excellence. The product is robust and is insensitive to the variations in the noise factors. Now we will try to understand maybe design for manufacturing and design for assembly in today's discussion with the help of certain examples. Now what is design for manufacturing? It is ease for manufacturing. So DFM is a method of design for ease of manufacturing of the collection of parts that will form the product after assembly. So design for manufacturing means that if we have a product that we want to manufacture, the design should be such that it is easy to manufacture. We will try to see that how a set of guidelines can help us to achieve this objective, that the design is easy to manufacture. So here we are trying to optimize the manufacturing process. We are trying to design the product in such a way that it is easy to manufacture. Now design for manufacturing is a development practice emphasizing manufacturing issues throughout the product development process. Usually this happens at the manufacturing stage only, but here you can see from this sentence emphasizing the manufacturing issues throughout the product development process, that is at the design stage also we are thinking that how this design will be manufactured when it goes to the manufacturing facility. It is not only that I am focusing on the design, that it should look good, it should be in this color, the profile should be like this, but I am also thinking that when this product will go to the manufacturing, which machine will be used to fabricate this, which tool will be used to fabricate this, which tool will be used to finish this. So I am thinking of the manufacturability of the product also during the design stage only. That is the beauty of this concept. Successful DFM results in lower production cost without sacrificing the product quality. So if we ensure that the design is easy to manufacture, we save lot of cost and the quality is also consistent. So these guidelines should be taken into account when we are designing a product. This is the entire manufacturing cost, we can say. For any manufacturing system, there are inputs, there are outputs. Now input can be raw material, labor, purchased components. Output is the finished good or are the finished goods. Now you have equipment going into the system, information, tools, energy, supplies, services, raw material, labor, purchased component, everything going into the system is an input and everything will entail some amount of cost. So this is the cost that goes into the system and it comes out in the form of the finished goods. And there will be certain waste also or discarded or rejected or discarded goods. Now what are the manufacturing costs of a product? We can see the manufacturing cost of the product can broadly be components, assembly cost and the overhead cost. From the previous slide only we can break down the manufacturing cost into its individual constituents or components. Components can be standard components, components can be customized components. So if they are standard components, they will be procured from the market. If they are customized, we have to manufacture them. Then for a customized component, we need to have a raw material. There will be processing cost, there will be tooling cost. Similarly for assembly, tooling means sometime processing can be the actual machining cost, but tooling cost can be the specific tool or a fixture or a jig that is used, which there can be difference, or in many cases tooling can also be included in the overall processing cost. In certain plastic parts, the tool may have a different perspective because the tool is the main, we can say, focus of, or the die is the main focus of the plastic manufacturing process. So maybe depending upon the type of manufacturing, we can bring them different or we can club them together also. It hardly matters, but this is just to understand that what is the manufacturing cost for a product. Then the assembly cost, labor cost, equipment and tooling cost. Overheads can be support, maybe consultants or the other support, and the indirect allocation cost. So this is just a general description of the manufacturing cost of the product. Now we have to ascertain that this cost is do not overrun and is easy to manufacture, means the cost should also be minimum. Now this is a little bit of explanation of manufacturing cost. I have already explained component costs, parts purchased from the supplier, custom parts made in manufacturer's own plant or by suppliers according to the manufacturer's design specification. The first one is component cost. Assembly cost already discussed. Overhead cost, support cost like material handling, quality assurance, purchasing, shipping, receiving, facility. Indirect allocations not directly linked to a particular product but must be paid for to be in business. So these are the just a brief fixed cost incurred in a predetermined amount regardless of the number of units produced, that is setting up of the factory, work area or cost of an injection molding machine. Variable cost incurred in direct proportion to the number of units, for example the cost of this. Fixed costs, variable costs are very common terms used in the break-even analysis. Whenever you draw the curve, you will use these curves for fixed cost, remaining horizontal, then variable cost depending upon the number of products produced. So in general we have tried to understand that what is the cost structure of a product when we are manufacturing the product, when we are the design is not included here. So when we are saying design for manufacturing, we should know that manufacturing entails all these costs and how we should design the product so that this cost is somehow minimized and it is also easy to manufacture that product. So this is just a brief summary of the overall cost structure of the product. Now Why we have discussed the manufacturing cost, you may appreciate that because DFM method, now we are going to see the overall flow chart of the DFM methodology. We have a proposed design. Already we have designed a particular product. Now we will estimate the manufacturing cost. We know what are the costs that are involved in manufacturing the product. Then we will see, reduce the costs of the component. We will use our creativity, our innovative bent of mind, and see that this component is necessary, how we can redesign it, but keeping the quality, performance, reliability, durability, ease of service, everything into our mind. We are not going to compromise on anything, but we will try to reduce the costs of the component. We will try to reduce the costs of assembly. We will try to reduce the costs of the supporting production. So we will try to reduce the costs wherever possible for the proposed design by coming up with a new design. Then we will consider the impact of DFM decisions on the other factors. Other factors can be, as I have already told, the performance factors, and then recompute the manufacturing cost. If it is good enough, we can say okay, the new design is acceptable design. If it is not good enough, again we will go and estimate the manufacturing cost, and then again the cycle will repeat. So basically the overall summary of this flow chart is that for DFM to be successful, we will analyze each and every product from the point of ease of manufacturing. We will try to reduce the costs wherever possible. Sometimes it may so happen that initially when we are proposing a change in the design, the cost may be slightly higher, but the process is faster so that it can produce more number of parts, so the overall production cost may become lower. So it is not always, maybe when the cost is lower we are achieving our target. Sometimes the cost may be higher also, but the life cycle or the overall cost of the product or the manufacturing is lower, and therefore we may propose a change in the design of the product. So here we can see we have a proposed design. We see how we can redesign it in order to achieve our target of ease of manufacturing in consistency with the cost structure of the product. We will only redesign the product from manufacturing point of view if we are gaining something out of it, if we are achieving some target. So ease of manufacturing, suppose there is a design which takes 10 minutes to produce and it requires 10 rupees for manufacturing cost. Now suppose we can redesign it in such a way that now it can be produced in 1 minute only, but the cost is rupees 12. So we are saving 9 minutes at the cost of rupees, maybe the cost is, initially the cost was rupees 10 minutes it is taking and the cost is rupees 10. In the second it is taking only 2 minutes, cost remains 10. So the cost remains same, 10 and 10 in both cases, 10 minutes and 2 minutes. So we say 2 minutes is better by the redesign, so that 8 minutes we are saving, 8 minutes of productive time we are saving. So similarly we have to do a trade off and see that where we are gaining. We will only modify the design if we achieve something positive out of it. In this case 10 minutes and 2 minutes, so we are saving 8 minutes, cost remaining same, so we should always go for that change in the design. In many cases if we are saving money also, so it is double benefit for us. Now for the DFM method, just a brief summary: estimate the manufacturing cost, reduce the costs of the component without compromising the performance, reduce the costs of assembly without compromising the reliability, durability, reduce the costs of the supporting production, whatever we are saying indirect costs, and consider the impact of DFM decisions on the other factors as well. So that we have to see here, maybe the time is not coming into picture, so the other factors can be the time, that if the product design is leading to less time for manufacture, that can be the other factor which can be taken into account. Now let us take a very simple example. It is a sheet metal product. You can see in a sheet metal design, specifying the hole sizes, locations and their alignment is very critical. So you can see hole size is critical, location of the hole is also very critical, because here this example is related to the location of the hole in the sheet metal. So it is always better to specify hole diameters that are greater than the sheet's thickness. So this is a sheet which has got a thickness of T, capital T. So the diameter of the hole should be greater than the sheet thickness. It is always better to specify the hole diameter that are greater than the sheet's thickness. This can be one of the DFM guidelines for manufacturing of or fabricating parts made out of sheet metal or the parts that require sheet metal operations. A mechanical engineer would be able to appreciate this point, that for every process there are a set of guidelines which are helpful to us. One of the guidelines given here is regarding the hole diameter in a sheet metal part. Spacing between the holes also matter. The center to center distance between the two holes is also equally important. Spacing between the holes also matters. It should be at least 2 times the sheet thickness, if not more. So 2 times the thickness of the sheet should be the center to center spacing between the two holes that are made in the sheet metal component. So distance between holes ensures strength of the metal and prevents holes from deforming during the bending or forming processes. For subsequent processes, this distance between the two holes will play a vital role. Now from this example we can see that only in one specific process, that is a sheet metal operation, we have seen at least 3 guidelines. So you can yourself imagine that how many such guidelines, rules of thumbs, heuristics may be available for engineers to take into account when they are designing a product. And if you take into account these guidelines, your product design would be such that it would lead to ease of manufacturing. There will be no problem during the manufacturing stage, no wastage of material will be there, and the product will lead to a successful product in the market. Here you can see red color, incorrect design. You can see the central distance of this hole from the edge is less than the thickness of the sheet. Therefore, we can say green color is the correct design. The distance of this hole from the edge is 1.5 T to 2 T, which is preferred. So this is one DFM guidelines for sheet metal component which can help us to design the product which will be easy to manufacture. So second part is the design for assembly. Now from design for manufacturing point of view, we have seen that if we follow the guidelines, our manufacturing will become easy and our product would become maybe more successful. From design for assembly point of view, DFA is the method of design of the product for ease of assembly. Design for manufacturing, ease of manufacturing. Design for assembly, ease of assembly. So optimization of the part or system assembly. So we will try to see that how many parts we can eliminate and we can make our assembly process simpler. So quickly let us see. DFA is a tool used to assist the design teams in the design of products that will transition to production at a minimum cost, focusing on the number of parts, handling and ease of assembly. So we have to see what is the number of parts going into the product, how we should handle them, that is their handling should be easier and their assembly operations in totality should be simpler, easier and cost effective. So that is what is our target when we are designing the product from ease of assembly point of view. Now design for assembly principles are given. I think quickly I will read these, not much requirement to explain each point in detail. Minimize the part count, that is number of parts can be less or tried to be minimized. Design parts with self-locating features. So self-locating means there should be some feature which will help it to be located at its desired position. Design parts with self-fastening features. So if you club the two things together, it should stick to each other. Self-fastening should be there. Minimize reorientation of parts during the assembly. So once you orient it, they should not get reoriented during the assembly process. Design parts for retrieval, handling and insertion. Emphasize top down assemblies. Maybe top down means the sequence of assembly operations should be very structured. Maybe you can start from a bigger part, then the smaller part, then smaller, you can build on the assembly in such a way. Standardized parts, minimum use of fasteners. So standard parts should be used. Encourage modular design. Maybe minimum number of parts should be there. Modular means single. Design for a base part to locate other components. As I have told in the top down approach, sequence is very important. And design for component symmetry for insertion. So suppose a square part has to fit on a square part, both parts can have a square geometry so that it is easy to fit. So the component symmetry also is important. So if we take into account all these points or design for assembly guidelines or principles, our design would be easy to assemble. Now here we can see one example. Optimal design for a thermal gun sight reticle in a US tank made by Texas Instruments. So this is one example, has been taken from a book, Boothroyd, 1994 it was published. So here you can see one design and you can see the number of fasteners going into the product and the complexity of the design. So there are large number of fasteners here, and as per our guidelines you can see we should design parts with self fastening features, and somewhere it was written that we have to minimize the fasteners. Standardized parts, minimum number of or minimum use of fasteners. So as per this guidelines, if we redesign this part, you can see how simpler, same objective met, same functionality, no compromise in the performance, simpler part. So redesigned thermal gun sight reticle, simpler to assemble and less to go wrong. So chances to go wrong is less. Foolproof design, easy to assemble as well as less number of fasteners, will definitely take less time. So let us see what are the advantages of this new design. This is the measuring the improvement, the old design and the new design. Now you can see parameters of comparison. Assembly time improvement by 84%, less time consuming. Number of different parts, 66% improvement. Original has 84 parts, 24 parts, number of different parts. Redesign has only 8 parts. You can yourself see it has got less number of parts. Then total number of operations, in original 58 assembly operations, in the new design only 13 assembly operations. So metal fabrication time also 71% reduced, weight also 45% reduced. So you can see by following a simple design guideline, that is for easy to assemble product, we should have minimum number of fasteners and a redesigned part with this guideline, that simpler, easy to assemble, top down approach, minimum number of fasteners. So if we follow DFA guidelines or design for assembly guidelines, you can see for yourself what can be achieved or what is the order of improvement that we can achieve. Now this is another example. This is the original part, very complex, so many number of fasteners there, so many number of parts. So here you can see redesigned part, less number of fasteners, easy to assemble. So this is redesign of a motor drive assembly following design for assembly analysis or design for assembly guidelines. So you can see different designs we can redesign based on the guidelines, and the redesigned part can be much simpler, much cost effective, much better in performance as compared to the original part, which is also the basic concept of value engineering. So what can be the differences? These differences I will touch when we will go to the DFMA guidelines in the next, we can say, discussion. On week 4 we will discuss DFMA guidelines in detail, and we will see what are the guidelines for manufacturing of part when it has to be manufactured by casting or forging or welding. So all those details there when we discuss. I will come back again to this slide. What is the difference between design for assembly and design for manufacturing? This is the we can say cost of assembly versus cost of part manufacture. This is important. Here you can see when the part count is reduced, part count reduction, your green line shows your savings in the assembly operations. So when your part count will be reduced, you will save money because your assembly will become easier. You have to assemble less number of parts. Similarly, for part manufacturing saving, when your parts will reduce, you will also save some money. But here there is an optimum value. Why there is an optimum value here? After that our savings are going down. See, there is optimum value for the savings. If we can draw a straight line here, and after this is going down. So our part savings are going down. Why? Because by reducing the number of parts to a very critical or very lower value, which means that the complexity of the product will increase to such an extent that the manufacturing will become very difficult. So sometimes in order to manufacture it easily, a complex part is divided into simpler parts, so that all simpler parts are easy to manufacture. But when we want to reduce the number of parts, as per the DFA or design for assembly guidelines, the parts will reduce, but the individual parts may become more and more complex. So that has to be taken care of. So after a optimum part reduction, if we further reduce the parts, the savings potential comes down. But the overall, if we follow the DFM and DFA guidelines, the overall savings are positive only, maybe up to a particular number of part count, beyond which the savings potential goes down. So overall we can see that these are important concepts. We have taken 3 examples, one in DFM and 2 in DFA, where it has been proven that the guidelines are helpful in not only ensuring the easy manufacturing and easy assembly of the product, but also helpful in saving the other benefits also, like weight is also saved, time is also saved, money of course is saved. So it has become maybe profitable for the company to adopt these guidelines, to follow these guidelines in letter and spirit, so that the overall cost structure of the product improves and product becomes more and more competitive in the market. So the companies that follow these guidelines have a competitive advantage in the market, because their rejections are less, the cost is also competitive, as well as the time for manufacturing is maybe saved, and they are able to launch their products with a much more, we can say, agility as compared to their competitors. In the next lecture we will see that what are the other tools which are helpful to us in designing the product, which will help us to design a product which is going to be successful in the market. And our focus primarily will be on the ergonomic aspects of product design. Thank you.